Now let's put these formulas into action and do a few examples of evaluating various situations involving simple and compound interest. Starting with simple interest. So simple interest is a type of interest which technically is not exponential at all. It's actually linear growth based on the formula P plus PRT. And basically simple interest is a type of interest where every month or year or whatever, it will grow by the same percentage based on the original principal. And basically the interest rate, the percentage, is just going to be the slope of the growth growing at the exact same rate all the time. Now, usually interest does not grow in this way in most circumstances, but occasionally it could. And let's just see an example of where it could happen. So sometimes government or corporate bonds use simple interest to calculate the future value of the investment. And basically the idea here is that you're going to be investing in the government or a corporation, giving them money with the promise that they will pay you back more later. The face value of the bond is going to be the amount you get, which we often refer to as upon maturity, which is just like a way of saying, well, in the future, after it's done growing, what will it be worth? So let's calculate the face value of a 10-year municipal bond that has an original cost of $1,250 with an APR of 3.25%. And basically the starting value will be our principal, how much we always invest. The interest rate will be R, which we, again, will need to convert to a decimal. And we can plug all those into the simple interest formula because we're told that it's using simple interest here. And 10 years will be our time frame. So plugging all that in, the future value of the bond should be equal to $1,250 times 1 plus 0.0325. Remember to move that decimal place twice for the interest rate multiplied by 10, which is the time frame. And another way of looking at this is that the interest rate is like the slope. T is like x. So if you're thinking about y equal mx plus b, basically I have my slope, I have my x, and I have my intercept. It's just built a little bit differently based on the fact that it's starting at the principal, the y-intercept. And technically the slope would be the principal times the interest rate. But anyways, at the end of the day, I could just toss this all into my calculator to see what I will get. And basically the future value of this particular municipal bond will be $1,656.25. So basically after 10 years, I will have that much more money after all is said and done. And the reason, we're looking at this is, say, for example, you were thinking about investing in a particular bond or whatever it might be, you have the tools to kind of analyze what your answer would be. And the question is, well, is it worth it? I can see that I have the straight amount of interest would just be the amount of growth here, which would be about $406. You could answer the question yourself: is it worth it to invest $1,250 for the course of 10 years to gain $400? Now these are very, very safe types of investment. I would probably say this is not worth it because that is not that big of a growth. But again, the higher the amount you invest, the more interest you'll gain. And it basically, the future values depend on a lot of things: the interest rate, the time, and the principal. All of those things factor into how much money you can gain via interest. And obviously for most people, the principal is something that they have a certain amount of money they want to invest. That's usually not a variable. But what is the rate of the time. You can get various interest rates for various different types of accounts, and you can often choose how long you want to have it happen. Anyways, let's now look at compound interest, because simple interest is actually not even exponential at all. But compounded interest is exponential, as we described before, and is as a result of repeatedly compounding those values. So let's say we were going to go into a bank and purchase what we call a certificate of deposit, which is basically similar to a bond. You go into a bank and you purchase this certificate with the promise that later it will be worth more, and the bank uses your money to invest, and they kind of give you back part of the amount that they earn from basically saving your money. But okay, so let's say we're going to invest $10,000 in a 3-year CD with a 4% interest compounded annually, and we'll again find the future value upon maturity. And basically, if we're going to be compounding it, we can use this formula instead. And what I wanted to do is look at, well, what's the difference in this formula and why does it work? But let's go ahead and start by plugging in the numbers. The future value is always equal to the principal, which is, we're investing $10,000 in this example, times 1 plus the interest rate, which is 4%, always in decimal form, divided by n to the nt power. So n is the component that is a little bit different about interest, which always, as I said before in the previous video, represents the number of times we're compounding the interest, which if it's compounded annually, that just means once per year, so n will be 1 here. And it's raised to the nt power, n times t, and in this case, we are investing for 3 years, which will be our x. So our exponent will be 3, and what I'm looking at here is if I simplify this, of course I could always plug this into my calculator, but what I'm looking at is 10,000 multiplied by 1 plus 0.04, which, you know, if I just put that together, that's 1.04, and raised to the 3rd power. But basically, it's very similar to a simple interest formula where I'm taking the principal and I'm multiplying by 1 plus the growth amount, basically the amount of the growth rate. What's different, though, is instead of adding 3% 10 times, I'm going to be repeatedly multiplying by 1.04. And what this will do is every year it will give me, well, if I start with $10,000, we can kind of see this in action. After the first year, I'm going to have 4% growth, which will leave me at $10,400. Then, since it is compounded, I take my new amount, which is my balance after 1 year, and I'm gaining 4% on that. So it's going to grow by a little bit more in the next year. And in the 3rd year, again, I'm going to take the balance after 2 years, multiply by 1.04, which will give me the balance after 3 years. And what I'm going to wind up with is approximately $11,248.64. And again, what I'm trying to illustrate here is why is this exponential and what's the difference? When it was linear, it was growing by the same amount each year. It was growing by a flat 3%. But when it's exponential, it's growing by 4%. But because it's compounded, every year it's being multiplied. And by result, we can model this by an exponential function because the principal is not static. And it will account for that if we just use an exponential function. But notice that the base is 1.04. We could think about that as our exponential base, and really the time frame is like the exponent in that exponential function. Now, if it were compounded monthly, the only difference would be that instead of compounding it once per year, we would change that to a 12, and it would result in a slightly different base in a slightly different exponent. And so we would wind up with 10,000 and 0.04 divided by 12. It probably is better to just type this all out into the calculator, but let's just kind of try to explore why this is happening and what's actually going on in there. But 0.04 divided by 12 would be 0.003 repeating, so I'd have 1.03 repeating as my base, and this would be to the 36th power. Oops, I missed a 0. And basically, since I'm doing it every month, what's happening is I'm actually doing this repeated multiplication quite a bit more frequently. The base interest rate, which we often refer to as the periodic interest rate, is divided by 12 since I'm doing it once per month instead of once per year. So the interest rate is a lot smaller, but I'm doing it a lot more frequently. So I can kind of think about the exponent as the frequency of how many total times is it, we often refer to as the number of periods of growth in this account. Again, you don't need to know all these terms. Just, you know, this is all very basic finance. And I think it's really important just for, in general, to learn all this, even if it's not covered too extensively in our book in this chapter. But anyways, this would leave me with 10,000. And we could always just type in the baseline formula in here as well, which would be that. And it would leave me with approximately $11,272.72. And notice, like, another reason I wanted to do all these examples is sort of compare and contrast. When I'm looking at this example versus this one, when I'm compounding it more frequently, it's a little bit different. Basically it's a different function. It's got a different base, a different exponent, different rates of growth, but they all have a similar result. It's not like monumentally different when I'm compounding. And really, another reason I wanted to show you guys all these different examples is just to emphasize, well, if I'm looking at the same situation and I'm changing the type of compounding, what is the real difference? There is a little bit of a difference, but at the end of the day, it's not too significant. It's just kind of, I'm changing the parameters, all of those things factor into growth of money. But at the end of the day, exponential growth works in a way where over time, it's going to be growing faster and faster and faster, because as the principal grows, so too does the amount of interest I'm gaining. Whereas with simple interest, it's just going to be gaining the same amount every year, much, much different. And people who get in trouble with debt often don't realize that credit cards or home loans they grow exponentially. And if you stop paying them off, it's going to only get harder and harder and harder to climb out of that hole. You need to be very careful about putting yourself in debt. In a lot of cases. And last but not least, continuously compounded interest. And this is kind of playing back into what I was talking about E from the previous slide and being the end behavior of this particular function. But one thing about the compound interest formula is it's a pretty complicated formula. There's all these different variables and there's n. N is kind of the most confusing part of it. But if you kind of look at it as 1 plus 1 over n to the n power, notice it's got a very similar structure to this formula from the previous page. And if you remember what I was saying last in a video or two ago, what happened as n approaches infinity is this basically this whole algebraic expression morphed into that very specific number e. And that's exactly where this compounded continuously interest formula comes from. That's what I wanted to elaborate upon. Because if I were to, like, and basically another question is, well, I could compound it once per year or 12 times per year. I could compound it every single day of the week. But what if I wanted it to just be continuously growing in an exponential behavior? How would that work? You could think about that as being compounded like every second of every day or 1,000,000 times a year. But basically, looking at that n as, say, 1,000,000, what would happen is this formula would morph into this formula, and it becomes quite a great deal simpler, where e is the base of the expression, r actually moves into the exponent, and otherwise it's basically the same formula. And so cutting out some of the calculus involved in actually proving this, basically what I wanted you to see is the result is what we call a continuously compounded interest formula. And we can use that to figure out, well, what would happen to this growth if it were just compounded continuously for its entire lifespan. And again, looking at the same example, let's see what would be different about it. But basically, we would just use that other formula, F is equal to PERT, or PERT is kind of an easy way to remember it. Which would be, well, my starting investment principal times E, which again is about 2.72, but I would just use the calculator for E because it's more accurate, and raise that to R, which is 0.04, times T, which is 3. And notice that it's kind of weird because the interest rate moves into the exponent, but that's the general way that it will work with exponential functions, is if you have exponential growth, the growth rate of the pattern is always multiplied within the exponent. And when we look at more models in the coming weeks, we'll see more about that. But in this particular case, we get 10,000 times e to the 0.04 times 3. And that would leave me with approximately $11,274.97. Again, not substantially different from compounding it once per month. But anyways, it's kind of like I like to call it the speed limit on exponential growth. If you compound it more and more and more and more and more, it will approach this pattern, which is kind of a way of helping to see why e to the x is so important. It models a behavior with an exponential growth rate where it's literally growing constantly all the time. And it's important, say, for example, in the sciences, because if we think about how things grow in decay, they don't tend to grow like like say for example, imagining a flower growing. It's not going to grow once per month and just sort of grow, 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 which is sort of like what happens if we imagine our money growing, compounding every month. Once per month, we have this growth applied to it. Bam, it's growing, it's growing. But usually it's growing continuously over its lifespan, modeling a more smooth curvature. And that basically E is the mathematical speed limit to it. And there's a lot of other reasons why e to the x is important to calculus, which we're not going to get into in this class, but it's the most important exponential function, has a lot of unique properties. Anyways, that will wrap up this one. Sorry, it got a little bit long.